talking today about noisy images and how to quiet them.
And you're allowed to take your mask off if you want while you're speaking.
You know, I feel like I should just because, but
That's fine.
it's just a matter of showing them the right, respect for the law here, right? So, at any rate, basically, start about thinking, what does a camera do? Right? So, a lot of times people talk about cameras capturing light. But that's not really what we use cameras for most of the time. We also don't necessarily want to talk about them making pretty pictures, because pretty pictures that have nothing to do with what you actually point to the camera at are not really what I'm interested in. I really want to capture what the scene looks like. And what the scene looks like is basically what it looks like to me as a human being. So, for example, I don't see things like photon shock noise, which we'll be talking about. So, if we take a look at some very straightforward images, this is actually an image from GP Review. We'll flip from it. You can see here's an original image, and this was shot at a high film speed. So there's quite a lot of noise there. Right? And if you do the usual sorts of things, trying to reduce that noise, you can do things like, for example, this is wavelet noise reduction, which you can see definitely reduces the noise, but it kind of makes things blurry and smeary and not really very pretty. And then you try and compensate for that by sharpening, and it doesn't really get you back something that looks like the actual scene. If we compare that to actually modeling the noise and trying to fix things based on repairing the noise, here's what we're getting in the current tool. So basically from that original to the one in the lower right corner. Now, in order to do this, we're modeling the noise in fairly high detail. So let's talk first about what kind of noise we have. Well, basically, as I started to say before, there's photon shock noise. So light itself is actually quite noisy. Basically, emission of light from any light source is a statistical process. And when you have a relatively small number of photons, you're going to get a lot of graininess, a lot of basically uncertainty in the value of a pixel. And even though people may think that that's probably not a big deal because there must be lots and lots of photons, when we're talking about relatively high film speed captures, an individual pixel might have as few as just a couple of dozen or a few dozen photons hitting it during the exposure. So we're well into the range where basically the granularity that you're seeing isn't even the camera's fault. In many cases, it's literally that the light isn't sufficient to sample it in the time interval that you're collecting photons. Taking that a step further, the way the digital cameras actually work is that you have an analog sensor. And the analog sensor is basically summing roughly a unit charge for every electron that it absorbs. Now, that sounds great. It sounds like we should get a very clean measure. But there's this thing called the quantum efficiency. And the quantum efficiency is basically what fraction of the photons actually deposit charge. And that is not 100% either. So we've got another statistical process in there that's causing noise. There's also things like fixed pattern noise. Not all pixels are created equal. Some of them are a little bit better than others, and I mean within an individual sensor. So basically what you've got, actually in modern sensors, it's not uncommon to have literally hundreds to thousands of bad pixels. Right? Why would that be? Well, hey, if you've got 36 million of them or something like that, having a few hundred bad is kind of negligible. You can basically, in software, hide the fact that you have these bad pixels, right? So there are fixed pattern noises from moderately bad pixels. Dynamically, there's the issue of dark current, which is basically leakage when you're looking at a dark portion of the scene. And that leakage is very related to things like what temperature the sensor is at. So it's a very dynamic thing. It's not something that's the same from one shot to another. We also have issues like read noise, which again can vary because of things like, for example, the fact that you've got this very weak analog signal that you're digitizing with this pile of high-speed digital logic wrapped around it in the camera. Right? So you've got basically a very high noise source very close to these wimpy analog signals. So again, we get a bunch of dynamic things that can go wrong in the camera. We also get various processing artifacts from digitizing those values. You might think that if you have raw images from a camera, they're really literally just the raw digitized values from that photodetector, but that's not quite true. In most cameras, they're actually processed in a variety of ways to do things like take out the bad pixel data. They're also processed to do things like scale things down to values that are in a smaller representation. So rather than having, for example, 16-bit or 14-bit values, you might send them back down to 11 or 12 bits. Then on top of that, there are often encoding processes that are not really lossless. So you can have all sorts of things that are basically corrupting into the digital domain. So what it boils down to is all of these are things that we see as noise in an image, and they're very complicated, intertwined in weird ways, very dynamic for some of these. So the point is, we want to be able to model the total impact of noise, and we want to be able to essentially subtract out that noise, use that recognition of what the noise is, to be able to return us back to the ideal pixel values. And keep in mind that the ideal pixel values are something that is actually more precise than what the light alone would have us detect, that we had perfect detection of the light. Because the light itself is noisy. We want to be able to take care of that noise as well. Right? So when I talk about my noise model, I always talk about it in terms of having an ideal pixel value, and then you have the value that you actually read. And the point is, no matter what is causing a discrepancy between those two, you want to be able to come back to that ideal value. Now, how do you get at this ideal value if the light is not even there to create that if you were to be a perfect sensor? Well, one of the tricks that's very commonly used, and this is something that we've used to very good effect, is the idea that if you keep sampling over a longer and longer period of time, basically things like photon shot noise tend to go away, statistical variations on other things tend to go away. So the average value for sampling the same pixel for a static scene over a long period of time basically converges on what should be the right value. Not always, but mostly. So with converging on the ideal value, you can actually get a significant improvement. Just to give you some idea, this image over here is essentially one where it was shot at 960th of a second on a little Sony camera with a 1-inch sensor. And as you can see, it's very grainy, very coarse, because basically it's a small sensor and not a whole lot of photons there, a lot of noise. We take a look at the image on the side. That's basically created by taking a whole series of images, in that case on the order of 1,000 images, and based on a noise model from that, essentially saying, well, so long as the pixel value is the same, or the same within my error bounds, so for a particular pixel, over multiple frames, I can average across multiple frames for each pixel position. So this creates a much, much better image, much lower noise, higher detail, all these good things. Now, how do we create this noise model? Well, the way that we did it for this is actually the idea of creating a probability density function, a PDF. So what you're really doing is you're saying, okay, I've got this noise, and what I'd like to do is I'd like to be able to know, roughly speaking, for each ideal pixel value, what range of other readings can I get representing that? And what is the probability that if I get a reading of, let's say, X, that the value is really Y?
This isn't per pixel, it's across all the pixels.
It depends. In some cases I do it across, I do it for each individual pixel, but the model I'm going to be talking about here is basically for pixels that have a uniquely identifiable set of characteristics. So you can think of for each color channel worth of pixels. But rather than thinking of it that way, let's show you the actual picture. So here's what my PDFs look like. So basically, if we take a look at this image on the side here, what you see is the Y positioning in this image is essentially telling you the ideal value, right? What the average value was. Now, if I had no noise, what I would have is the X value is just basically kind of a histogram of what values occurred that were related to that average value. So what you would see is that essentially, for the points up at the top, you can see for the relatively dark portions of the scene, I've got a lot of skew there. And then basically down at the bottom where it's got that gray, it looks like it's a perfect straight line. There's really no divergence there. Let me just say, the gray area is actually where I had no data. So that's actually just kind of a baseline. So you can see there's actually a little bit of smearing around that. It's not just a nice thin line, which is what we have if there were no noise, right? Now, well, did you happen to have a laser pointer, by the way?
No.
color channels, red, green, and blue, and there's no reason to believe that the red, green, and blue would actually have the exact same noise response. So this is actually computed separately for each of the different color channels. And then here I'm just showing you that as a 3-color image, combining it so that it's a little bit easier to look at. Does that make sense? Okay. So what does this do? Well, just doing this with, for example, JPEG images or captured from video, here's the kind of thing that it can do. So here's an original video that was shot at 240 frames per second. And you can see it looks pretty coarse because basically 240 frames per second on the little camera that was used for this, there isn't a whole lot of data. Basically, there's very poor quality for each of the samples, and you're seeing that in the roughness here. Here's what happens when I simply average the pixel values, where basically my noise model says that the pixel value hasn't actually changed, the ideal value hasn't changed, it's just been varying with the noise. So what you can see is just by doing a simple averaging within an envelope that tells me that the scene hasn't really changed, it's just noise that I'm looking at, gives me something on the order of maybe a 3-stop improvement in the dynamic range and in the signal-to-noise ratio. So very significant change. Now that's what we were doing way back in 2015. We've gotten better since. So our new model is, rather than working with things like JPEG images, we're actually working directly with raw image files. Now the raw image files are not full-color images as you would expect them to be. Basically, each pixel is only sensitive to one color of light. There's a color filter ray in front of the pixels. So trying to sum this up is a little bit more complicated than it seems. I've drawn this here as or I should say, I include this here as an RGB image, but in fact, we're actually doing this for 4 color channels, not 3. And I'll show you why in just a moment. It has to do with this idea of each color channel that has a unique pattern of neighbors is basically a unique color channel to us, even if a couple of them happen to be the same color for the filter that's there. Right? The ideal value still is the Y coordinate on that. The X value is the measured, and you can see again it's normalized as a histogram for each line across. Okay, so what do these color filter arrays that impose the color on a sensor really look like? Well, basically, the most common is that first one, which is often known as the Bayer filter. Basically, a pattern of red, green, and blue that has 2 greens for every red or blue. And there are a variety of other schemes that are used. You can see here, for example, green, magenta, yellow, cyan is very commonly used, or used to be commonly used, because it's a little bit lighter in color, so you get a little bit more light through. But on the other hand, you really want red, green, and blue, and that has to be derived from those colors, so you've got a little bit more noise potentially in the processing of that. Then we've got some things that have basically 2 different types of green, and then you can also see one of them where you replace one of the greens with a white, so that basically you get a little bit higher sensitivity by not having a filter blocking that at all. Right. Well, all of those can be modeled as 4 color channel, because it's just a repeating pattern of 2 by 2s. Right. Some cameras don't do that. So for example, Fujifilm X-Trans has this 6 by 6 repeating pattern. Our software would currently deal with that. Basically, if we were going to deal with that, we would have to have more than 4 color channels, and it just didn't really seem to be worthwhile making that special case to be the driver for another code construction. Okay, so we've got this idea of the PDF. Now, how do we actually create that? Well, essentially, in TIC, which was the thing that we had doing this back in 2015 and so forth, what we did was we basically shot videos of static scenes, and then we averaged for each pixel, and we actually computed what the ranges were and basically histogrammed for each pixel over time, and then that basically all got summed to produce our PDF. Very straightforward way to do it. It makes a lot of sense. Very empirically grounded. The problem is, you don't really want to have to shoot a whole bunch of frames of a static image in order to be able to build up a noise model. I want to be able to just have a noise model that's reasonable looking at a single image, single capture. So we tried doing that in the original version of something called Creamy, which is back in 2016. And the way that we did that was that the software basically looked for regions of the image that happened to be smooth shaded, looked like it was a continuous thing. Then it would measure noise for those, and then it would interpolate between those to get us a complete PDF for all the different color for all the different values for all the color channels. That was fine. The only problem is, what if your scene doesn't have a whole lot of patches of solid colors? Then we don't get a good model, right? So the new version of Creamy, which is really what I'm talking about here, what we do is we take that a little step further. We say, well, if you think about it, especially if we're sampling at the Nyquist rate or better, every pixel should have a pixel near it of the same color that's basically representing almost identically the same ideal value. So if on average we put those things together, that should actually give us a distribution for what the possible actual recorded values are for each of these ideal values. Now, it's not really correct, but it turns out to be more than close enough. Now, once we get something like that, let's say that, for example, I find that a value on the red channel happens to be 25 here, and its nearest neighbor, let's say, was 27. What I would do is I would say, okay, when I'm building up my histogram, which I'll convert into that PDF model, I'll essentially take everything between 25 and 27 and say, okay, that could occur once. And that basically gives me my probability density function, just summing up all of these increments of a square for the region between pairs of neighboring values. Does that make sense at all?
Now, what I'm lost with is once you've got that probability density function, how do you apply it to an image?
Well, that's coming in one more slide.
Okay.
Okay. So here are a few that were generated by doing this model. Right? Basically, this is generated by the process I showed you. The Canon Rebel XT at ISO 100, almost noiseless. Not noiseless, but almost noiseless. You can see there's a little bit of thickness to that line, but not much. An iPhone 7, even though it's at a very low film speed, pretty terrible. Why? Really small sensor, really small pixels, not a lot of photons. Right? And the A7C is a high-end Sony full-frame camera, very modern, but look at the film speed. 200,000 film speed. That's one of those things that, 20 years ago people would have said, there's no way, that's just impossible, there's no light there. And as you can see, they're half right. There's an awful lot of variation, there's an awful lot of noise. All right, so how do we repair the data using this information? Well, there's a technique called texture synthesis. And texture synthesis is normally used to essentially create a credible pattern to replace a missing portion of an image. So, for example, if I have some bad pixels somewhere, I can use texture synthesis to replace the values for those bad pixels. Now, what we originally did in Creamy and in Carwy, which I'll tell you a little bit about later as well, was that essentially we used a texture synthesis algorithm to basically not actually replace pixel values, but to just tweak them within the error bounds that we measured. So if I had, for example, there was a relatively high probability of values from, let's say, 25 to 27, and I didn't know exactly what the value was in there, what I would do is I would pick the value there that was most consistent with the pattern matches that I saw for similar surrounds, similar patches in the image. All right. Now, that worked great, but let me just say that within bounds constraints, that's the problem. Our PDFs aren't really giving us bounds. They're giving us these probability drop-offs, right? So we were just calling some probability and saying, okay, well, if the probability gets less than 25%, we'll just say, forget about it. That's the line. Right? And that caused two problems. Problem number one is that in many cases, that basically meant that we couldn't make the big changes that we needed to make in order to remove the noise. Problem number two is that if you had a relatively large range that way, you had absolutely no idea where you should be within that range. It didn't really give you any guidance. But if we actually just use the probabilities directly, we get some very good effects. Basically, it gives us a weighting within that range. And it allows us to have, occasionally, pixels that change their value in very dramatic ways. So that's what we're doing now. So what we do is we weight the texture matches probabilistically, and essentially, every single pixel is individually replaced. So you can think of doing texture synthesis for each pixel in the image removed with all the other pixels intact. And that's how we generate our noise removed image. Now, some pixels change a lot and such, but it turns out that when they change a lot, they only change a lot because they had a very good probabilistic justification for changing a lot. So that's actually a big win. The texture synthesis algorithm itself, pretty straightforward. Basically, this is kind of a crude version of it, but you can see the idea is essentially you're just summing up these probabilistically weighted pattern matches, saying, which of these patches look reasonably close, and by that, reasonably close, I mean, essentially, you just multiply the probabilities for each of the individual matches within the pattern. So it's essentially using that model that we've generated, indexing by the pixel in the original pattern, the pattern around the one that we're trying to replace the pixel value for, versus the one that we're actually sampling a texture from. And just looking those things up, per color channel, etc., gives us a very good statistical model for exactly what the noise is. On top of that, we also add in a little factor where we basically lessen the weight as you get further and further away. Because if you think about it, in many images, the textures that are present in the image will change over areas in the image. So we want to bias it towards the things that are nearby. So the new CREMI implements this. The new CREMI implements this. And the way that it works is you use a Adobe dig converter to generate an uncompressed dig. So a digital negative, basically something that is a very portable format for raw data. Then we have about 1,200 lines of C code that actually implements the entire construction of the error model and the actual application of it as a texture synthesis. Then all of that is built into either raw to dig or DC raw, which knows how to process the basic decoding of these digs. And now the bad news, right? Sequential execution of this algorithm on a typical 24 to 42 megapixel image is on the order of maybe 20 to 40 seconds. The good news is, though, that's just pure sequential code running on one core. If you take a look at things that are competing with this, the AI methods that are closest to competing with this tend to run for about 2 minutes on a GPU with several thousand cores. So we're talking about something where even though it sounds like this might be very expensive, with a little bit of tweaking and such, this is actually efficient enough that this could be embedded in most cameras. This is not something that requires a separate GPU. There's a web interface version that we built. You can play with it. The interface is shown here. It's very straightforward. You just upload the image, and you've got a few little controls that you can use to determine basically the weighting on top of the probabilities. So you can essentially raise the probabilities to a power, so that you can essentially compensate for the fact that we're providing multiple probabilities to get this combined probability. And you've got another thing here, which is basically how far out should I actually accept textual matches. And then the last one is multiple passes, which we turned out to pretty much never use. So, does it work? Well, these are actually some of the examples that we have from the original paper on 3D. And you can see here that this first one at the top here, this is one of the Canon Rebel images at ISO 100. You can see there's not a lot of noise. It looks pretty good, right? But it's still kind of rough. With the original CREMI, it definitely made an improvement. But as you can see, there's still quite a bit of noise there.
Where can you show us? That's the second picture you're looking at.
Second one. Yeah.
It looks almost identical. You say there's improvement. What am I supposed to see?
So it's pretty hard to see on a screen like this, but if you look very carefully at some of the edges, you'll see that there are a few little glitchy things that have kind of gone away. It's just a hair smoother. But it's very little additional smoothing because remember, it's always bounded by that estimate of what the range is for the pixels, which is too conservative. But when we take a look at this last one, you can see it's markedly smoother. And not only is it markedly smoother, but you can probably see there's actually some little line artifacts on the edges on both of those first two images, on the top edge, the black there, which are not in the last one. And they weren't real. They should not have been there. That was noise. The one down here, again, pretty noisy image, slight improvement. By the way, I'm saying slight, but at the time this was actually considered state-of-the-art. This was actually considered very good back in 2015, 2016. This is a lot better. And notice that even though we've lost those granularities to it, we haven't lost the textural details. For example, the lines in that little section of the roof, you can see, are still there. Here's a few more images. It's a little bit harder to see these because these are well, at least the top one, because it's a relatively low speed image. It's not too noisy. But the iPhone 7 thing, I think it's very clear. We've got a lot of graininess here. We got a significant improvement with the original low graining, but there's pretty much no grain left here. It's just a nice clean image.
There also has blurred the logo on the back as well.
Not really. If you actually take a look at the edges, it turns out that there's nothing in the algorithm that blurs. So what it does is it synthesizes textures, so the edges are still there. So, and this is going to sound funny, but if you take a resolution test chart and you process it through this, basically the measured modulation transfer function contrast does not change. So even though it looks smoother, and you might say that looks blurry, the reality is that all that it did is just average this stuff out in a way that essentially preserved the edges, but it didn't actually increase the contrast column. So with everything else looking smoother and such, it might appear a little bit less smooth, but it's not really.
Excuse me.
Yes.
But how is it that in the first one, I can kind of understand what those characters are at the bottom, but then in the last one, I can't really tell?
Yeah, well, you've got a couple of contrast edges. You can't really read it. You're just seeing edges, right?
Yeah, but I can see them better than in the last one.
Yeah, but they're not real. I mean, you can't read the text, right? See, that's the thing. So if we take a look at some more images this way, for example, here, obviously, that's wildly more smooth. In fact, I would argue that's a little bit too smooth. So the model there was a little too aggressive. The parameters there, that 312, that 3 was basically raising the probabilities to the 1/3 power to compensate for the fact that my textures are basically multiplying probabilities for matching on each of the pixels. So 1/5 power would kind of be the normal thing that you would want for them to be actual legitimate probabilities. This is a little stronger than that. But basically, you can see it's smoothing things out very nicely. Maybe a little too aggressive, but not bad. But look at this. Here we have a variety of artifacts that are essentially coming from Moray. Now, the Moray is actually disappearing now. Why does that happen? Because in the texture synthesis, it basically recognizes the pattern and replicates it through what would have otherwise been the Moray.
Yeah. I'd like to see the original, because maybe there are those lines.
There are lines, but they look like this. And by the way, they don't look like that, so it still has a glitch. It's not perfect. Yeah.
So we're visually trying to see the differences right now. Is there a way of numerically capturing how much improvement there was?
Yeah, so the easy way to numerically capture it is to then actually compute the PDF for the finished image. And basically what you see is it's always got a significant narrowing of that margin. I don't happen to have one to show you right now, but basically it's very easy to do the comparison because we already have a thing that can create a noise model from an arbitrary image. And the output of this is the same thing as the input. It's basically a raw image, produces a raw image. Okay. Here's another little example. And I think it's very clearly doing a lot better here. So in case you're wondering what that is, that was actually the trees down at the bottom of Mount Rushmore in an incredibly poorly lit setting. And as you can see, there's almost no discernible information in the original image, but we've got something that definitely looks like trees in the last one. Here are a couple of test cases that are using different kinds of different kinds of color filter array patterns. And you can see, again, pretty substantial improvement on the old Canon PowerShot G1. And I don't know how obvious it is, but we've got a lot of kind of modeling here, a little bit of it here still, and here basically we've got a nice clean formation. We don't really have any of that here. So let's push it to the real extremes. What happens if we give it something that's just ridiculously noisy? Well, that first shot is actually the Sony A7C at 1600 film speed, which you can see for that camera is actually pretty reasonable. It doesn't have a huge amount of grain. The next one is the 200,000 ISO, and I think we can agree that's pretty much unusable. You take a look at the last one. I'm not going to tell you it's good, because because it's definitely not. But at least I see an eye there. Okay. So what you're seeing is the basic coloring is right. Most of the features are actually recovered. It's a pretty good approximation of that. Now, arguably, that's a road too far, so let's back up from that a little bit. Here's the top film speed that's supported on the Canon R5, which is a current high-end camera. And what you're seeing is first, this is at a low speed, so you can see what the image really should look like. The next one is actually what the capture is at ISO 100,000. Then that third one is what we're doing with creaming. Right. This is what was done by Remedy Professional, which is a commercial product. I actually went through trying something like 30 different commercial smoothing products that are all using AI algorithms. Remedy was one of the best ones, believe it or not. And if you look at this, basically all that it did was it essentially detected most of the noise as edges and enhanced the edges. Really not a very effective repair. AI image denoiser, I think overall did about as well as our technique, except it's very soft. It's doing a lot of smoothing. So you can see it's lost a lot of detail. It's also rounded some of the things. You can see here this doesn't have a sharpened edge as what we have to that structure there. The last one I think is absolutely amazing. And that's actually a commercial piece of software called Dietz Pure Raw. And there are two things to say about that. First of all, that's one that, as I was saying before, takes several times longer to run than the system that we have when it's running on a big fat GPU and I'm running on one core of a desktop. Right. The second thing to say about it is that it turns out that the stuff that it was trained with happens to include all of the test images that this has. So the fact that it did well on that is a little bit less impressive because it happens to actually have been in the training data. However, I will say, overall, it's a very, very good job on that. But I don't think that it's necessarily worth the extra time, and there's no way that that's going to be better than a camera, whereas our technique can be. Just to show you a little bit more scary stuff quickly. Car Week was something that I built back again around 2015 to repair a little defect in basically the compression algorithm used in Sony cameras back then. So here's an image of the IS&T logo, the Imaging Science Technology logo. The image that you see right next to that is the compressed raw format off the Sony camera. You see the little stair steps on the edges of the lines? Yeah, they should not be there. That last one is actually a raw image that's not compressed from the same camera, which is fine, because the raw images that are not compressed are much larger. It can shoot them only at a much slower rate, etc. So we really want to fix these to look like that. Well, the way that I did that was I computed a noise model that wasn't based on any of the stuff that I told you here. It was based on literally reversing the transformation to get error bounds by basically reversing the math that was used for the encoding. That worked pretty well. As you can see, there's the original, there's the repaired one, and there's the one that's just the raw image direct with no compression. So it does a pretty good job. The noise there, I actually had to directly impose more noise after the repair to make it look like it fitted in and not have additional artifacts from having basically repaired it too well, if you will. So you would expect that this is not going to be helped by the technique that we're using now, right? Because we're not modeling any of the static errors. We're not modeling things that are happening that way. Or are we? So that image on the end is what you get. It turns out that in order to see the noise, I had to turn up the gain on the exposures a huge amount. And basically, what happens is, I don't know if you can see, there's not a completely black background on that last one, but the noise reduction is so good on this that even turning up the background noise to the same level as I did in these images, that's what I get. And I don't know about you guys, but I don't see the little stair-step artifacts in that. Okay. So, in conclusion, basically, probability-based pixel value models do work. We've used them for years. They're getting better. There's more that you can do with them still, I'm sure. Also, let me just say, I'm talking about them working for taking a raw image and improving the raw. You can still do plenty of noise reduction after that actually modeled fairly well. The probability density image, I think, is fairly intuitive. It gives you a very quick overview of just how well the camera is doing. And let me say it's also editable. So if, for example, well, I wanted to embed this in a camera, maybe you don't want to actually have a computer model for every picture. What you can do is you can basically sample these things, and then you can use ordinary image processing tools to combine the images that are the error models. Right? So you can actually play around with these PDFs in a very cool way. The probabilities handle more extreme noise fairly efficiently, as you can see. It can be fast enough to execute in a camera, which is not true of things that are at least competitively good to it. And basically, the texture synthesis in this is actually simpler than what I had in the tools back in 2015 and 2016. So what we end up with is a very simple, untrained, deterministic algorithm implementing these repairs. And essentially, it does a good